So welcome back to session 2 out of 2 of Astrophysics with Lisa. 4 more speakers. I'll just introduce them along the way. Our first speaker is Matthew Moult from the University of Birmingham, and his talk is about enhancing gravitational wave population inference with deep learning. Please share your screen and go ahead.
Cool. Okay, thanks. Hi, everyone. Hope you're all doing well. Thanks for having me. I'm Matt. I'm a PhD student at the University of Birmingham. And as has just been said, I want to talk about some work we've done applying deep learning approaches to the population problem for ground-based sources. So far we've detected mergers across a range of source types, but I'll be focusing on stellar mass black holes. And we've detected sources across a range of masses, from a few solar masses, a few tens of solar masses, up to merger remnants, which are pushing into what you might call the intermediate mass regime, above 100 solar masses up to about 150 solar masses, let's say. And so the question now is, how do we form such sources? Because in the traditional kind of picture of isolated binary evolution, these heavy black holes are hard to form. And the way we're going to study now catalogs of detections made by LIGO Virgo is to do a Bayesian inference. And one of the ingredients in any kind of Bayesian analysis is a prior. So a prior model for what we think the distribution of these sources looks like. And the most common approach that has been taken so far is to use parametric models. So you kind of come up with some mathematical form that you think correctly describes the distribution of the properties of our binary mergers. So things like masses and spins. But this isn't so great in that it's not really astrophysically motivated. It's just kind of something we come up with off the top of our heads. A different approach is to take a simulation-based approach. So if you have some kind of forward model which produces a set of binary mergers, so for example, a population synthesis simulation, now we can fold in kind of all of the astrophysical realism which is feasible into our simulation, and compare this against the detections we make. The only problem is we want our prior to be continuous over the parameter space, whereas if we have kind of discrete simulations, we don't have that continuity. We only have a finite set of simulations. But what we can do is employ some interpolation or emulation techniques. And this is where deep learning is going to slot into our Bayesian pipeline. So now I'll just describe kind of the simplified set of simulations we perform, which aim to kind of describe the production of the heavier end of black holes we see with LIGO Virgo detections. So we set up kind of simple numerical simulations in which we start with a cluster of black holes, and cluster really is not really an astrophysical cluster, just kind of a collection of black holes which can potentially pair up and merge. And we have some kind of parameters which describe the initial masses and spins of that cluster of black holes, as well as an escape speed, which is kind of a crucial parameter for these clusters. And then we have some other parameters which kind of characterize the probability of pairing two black holes into a binary. So one by one, we draw black holes from these clusters, we pair them into a binary, and then we estimate the merger remnant properties using numerical relativity fitting formula. And one of the parameters you estimate is the magnitude of the recoil kick received by that merger remnant. Now, if that recoil velocity exceeds the escape speed of the cluster from which the binary came, it's ejected and it isn't placed back into the cluster. So it can't, the merger remnant can't then go on to pair up into a new binary. If on the other hand, the kick velocity is smaller, then we place that remnant black hole back into the cluster, and it can go on to pair again into a new binary and merge. And so this is what we call the hierarchical or repeated merger scenario, where merger remnants can then go on to form subsequent binaries and merge again. So your typical scenario is listed here, where we have two what we call first generation black holes, which are born from stellar collapse, let's say. And then second generation black holes, which have already undergone one merger and then may either merge with a first generation black hole or another second generation black hole, or there might even be high generations where multiple mergers have happened. And so these simulations result in distribution of the binary source parameters that we see in these four panels. So we model the chirp mass, the mass ratio, and two effective spin parameters. Chi-F is the usual effective aligned spin, and Chi-P is an effective parameter which characterizes the spin precession of a binary. And with our definition, this consistently incorporates both black hole spins. And so this parameter is now defined between 0 and 2. With sources above the Chi-P equals 1 line being signatures of that there's two precessing spins in that system. Okay, so we do many simulations, and we construct a discrete bank of binary distributions this way. Now we want to interpolate it so we have a continuous model rather than a discrete set of simulations. And so we use deep learning to do this. For each of 1,000 simulations that we perform, we first construct a density estimate over the joint four-dimensional space of these four source parameters with a KDE. And then we interpolate across the space of this prior density, which is a joint space over both the source parameters and the population level parameters, which we're going to constrain with our hierarchical inference. And we emulate this function with a deep neural network. And this consists of 5 hidden layers with 128 nodes in each layer, and some output which enforces our probability density to be positive. And I'll also point out this work by Case Wong, which takes a similar approach to performing this kind of deep learning based population emulation. For each of the mergers in our simulations, we also estimate the probability that we would detect them with our ground-based interferometers. And this can be used to construct what's called the detection efficiency, or the selection function, which is just the fraction of sources from a population you would expect to detect. And this is going to be very important because the mergers we see with our detectors aren't fair draws from the population. They're filtered through the biases imposed by our detectors. And so we need to account for that in the hierarchical inference. And so we also construct a deep neural network which interpolates this selection function across the population parameter space. And a final network we construct, which doesn't enter the hierarchical inference, but is useful in post-processing, is a neural network which predicts the branching fractions between the different merger generations I described. So what's the fraction of sources which are two first generation binaries? What are the fraction of sources where we have this mixed first and second generation, or two second generation sources? And then the remainder of sources which have undergone potentially multiple mergers. And again, we can construct a deep neural network which interpolates this function across the population parameter space. And so all of these ingredients get combined into our population level likelihood. So unlike your kind of usual parameter estimation, where you want to make inferences on individual sources, where we want to find out what are their masses and spins and redshift and sky position, etc. In the population likelihood, we want to combine all of the detections we've already seen and which have already had, their parameter estimation done for them. We define a new likelihood which combines all of those events, and as I said, we weight by this detection probability to account for our selection biases. And then we sample this likelihood surface with traditional nested sampling techniques, which many of you are probably familiar with. And so this is the result of that inference. These are the 6 population parameters which enter our model and which I haven't described. But essentially, these parameters are the inputs of whatever your astrophysical simulations are. So if you're doing population synthesis, for example, these are the inputs to your population synthesis pipeline. So you can kind of replace the 6 parameters we have here with anything which enters a some kind of population simulation. What's more interesting for us as astrophysicists is not necessarily the distribution of these hyperparameters, but they could in principle. So for example, you see one of the parameters in our model is a maximum mass in the fifth column here. And this is to model some cutoff due to pair instability supernova. So these parameters can be themselves of astrophysical astrophysical interest, but just the way our kind of simplified model of repeated mergers is set up, these are potentially less interesting. But maybe what we're more interested in as gravitational wave astrophysicists is the distribution, the population distribution of the binary source parameters themselves. So as opposed to here where we have a distribution of parameters, now we're looking kind of at a distribution of distributions. So if we take our inference on the hyperparameters and we fold in these Bayesian measurements which are uncertain, we can then go back and look at our population prior, which depends on those uncertain hyperparameters, and construct what do these distributions over the source parameters, so the masses and spins, look like. And this is where we make plots like this. So the panel on the left, I'm showing the distribution of all of the masses implied by our inference on the current catalog of stellar mass binary black holes. And because we split our population into a first generation of sources which form from stellar collapse and another population of sources which form through this repeated merger scenario, we can look at the difference between those two distributions. And what we find, as I said before, is this cutoff in the mass distribution, which is around 40 solar masses, which is kind of broadly consistent with predictions from supernova theory. But there's this extended spectrum of masses due to the heavy black holes we've seen so far with LIGO Virgo. And in our model, those are explained by this repeated merger scenario. And I'll
Matt, 3 more minutes.
Thank you. I'll explore that a little bit more shortly. And then we also look at the spin distribution. So for example, here I've just shown there's the distribution of our processing spin parameter, which kind of features multiple peaks and some minor modes, which in our model again is explained by this repeated merger scenario. And because we're modeling the joint 4-dimensional space, these aren't a product of independent distributions, it's the joint 4-dimensional space. We can look at how our parameters are correlated with each other. So for example, here I'm looking at how does our processing spin parameter vary with the primary mass, and how does it vary with the mass ratio. And so these kind of correlated features, which normally we don't model with parametric models, are intrinsically and easily captured by this kind of deep learning emulation pipeline. We can also model things which are inherent to the astrophysical environment hosting the black holes themselves. So in the left panel here, I'm showing what are the distribution of escape speeds of these clusters hosting black holes implied by our inference. And what we find is that though there's a preference for small values implied by this blue distribution, if we also look at the distribution of kicks received by first generation sources, what we see is that many of these kicks are smaller than the escape speed of the host environment. So around 40% of first generation sources receive kicks less than the host escape speed, which means they will be retained post-merger and can undergo repeated mergers. And then the final plot I'll show is this kind of post-processing. Once I have my hyperposterior, I can feed that into this neural network I constructed to predict the branching fraction between different merger generations and get a posterior on those merger generations. And in short, what we find that in our model, about 25% of sources aren't first generation. So at least one of the components has undergone a previous merger. And so that leaves me with my summary. So what I've shown is that we can efficiently emulate kind of simulated merger populations with deep learning techniques. And in the model I present here, the features that we see in the current catalog of stellar mass mergers, stellar mass binary black hole mergers, can be explained by this hierarchical merger scenario. And we employ kind of simple numerical simulations, but this whole pipeline readily applies to any simulation scenario you can think of. And so I've listed a few ideas for the future that I want to explore, but we can also explore applying these techniques not just to ground-based, to populations which are interesting for ground-based detectors, but also for the future space-based detectors like LISA. So thanks for listening.
Thank you very much. Also for keeping to the time perfectly. Lots of applause. Let me see. Oh, maybe I should have repeated. Please ask your questions either typing in the chat or raise your hand with the raise hand button of Zoom. If you're on YouTube, you can type your question there in the chat. This will be monitored. So with all these options, surely there will be questions. If not, I'll take the opportunity to ask one. This is a little bit far from my expertise, but I was a bit surprised about I think you said that these correlations that you could explore with this method, you couldn't do with parameterized models, but surely you can make a multi-dimensional parameterized model where you would get this too, right? Or
yeah, sure. So you can define some parametric model, and people have done this to explore parameter correlation. So you might have seen in the LIGO-Virgo papers the discovery of some correlation between mass ratio and the effect of aligned spin. But you still have to impose some parametric form. So you can say, oh, how does the mass ratio vary as a function of chi-f or vice versa? But you have to impose some kind of strict parametric form. Here, the correlations are whatever is implied by your simulations. So you don't have to make any kind of parametric imposition here. So I think the kind of parametric correlations are useful to discover correlations, but they're not so useful to describe why they are there.
Okay, thanks. I think in general, indeed, the fewer parametric models there are, the better, but it's not always easy.
Yeah.
Let me see. Anybody else who wants to ask a question? If not, let's thank Matt again. And let me remind you that via email or the Oxford Abstracts badges, you can still get back to Matt if you discover you have a question later.
Thank you.
All right. Thank you very much. We move to the second talk of the session by Shobit Ranjan on multi-band gravitational wave astronomy, measuring recoil kicks. Shobit, please go ahead.
I'll just share my screen.
Share your screen.
I hope it's visible.
Yes, and we can see you.
Okay.
And we can hear you. All right, go ahead.
All right. Well, hello everyone. I am Shobit Ranjan, and I am presenting my results on measuring recoil kicks with LISA and ground-based gravitational detectors. I recently graduated with a bachelor's from Delhi Technological University in India. This work I did at Vanderbilt University under the supervision of Professor Karanjani and Professor Kelly Holly Bockelman, in collaboration with Dr. Alex Neitz at AEI and Kurt Cutler at JPL. Coming to recoil kicks are primarily a result of anisotropic emission of gravitational waves from a binary black hole merger. These gravitational waves actually carry away angular momentum and energy, but they also carry away linear momentum, resulting in a kicked remnant black hole. The magnitude of kick is generally higher for precessing systems, and furthermore, the kick depends on 6 individual spin components and mass ratio of the binary. On right, you can see an animation from the GW surrogate model I have been using in this study. So after merger, after ring down, the final remnant black hole is kicked out from the center of mass of the system. So the projection of spins has been measured fairly well with the LIGO-Virgo observations, as well as individual masses and mass ratios, but a reliable measurement of recoil kick is something that has remained elusive. LIGO-Virgo collaboration did report the kick measurement in the GW 190521 paper, but the constraint was very poor. There are, of course, astrophysical implications of constraining recoil kicks. Some fine-tuned spin configurations can reach super kick values that is enough to escape out of clusters or galaxies. So, of course, naturally, the growth of black holes is associated with the magnitude of kicks, and this also has implications for galaxy evolution. We are trying to answer the question if we can constrain the recoil kick magnitude with multiband measurements in LISA and ground-based detectors. So this is a plot of two merging binaries. This particular case is for a binary resulting in a 150 solar mass black hole. Both binaries have same intrinsic parameters. That is, they have the same masses, same spin magnitudes, same projection of spins. The only thing that differ in is the azimuthal orientation of spins, or you can say the direction in which the individual black holes are spinning. These binaries will be visible in LISA starting at 10 millihertz, which is years before they are visible at a higher frequency in ground-based detectors. Both these binaries, although very similar at the beginning, have very different fates after merger. For example, one of the binaries ejected out of the system with a moderate kick of around 60 kilometers per second, while the other one is shot out at about 1,000 kilometers per second. So moving on to the method we have employed, we first start with the signal in LISA, many years before it comes down to the ground-based detectors. From this observation, we infer what we can about intrinsic parameters, such as the spins and individual masses. We then use this constraint while constructing the parameter space for running Bayesian inference on ground-based detectors. So in a way, we are shrinking down the prior for ground-based detectors to be aware of the region where LISA says that this particular parameter of spin or the mass ratio lies. So here are some characteristics of our analysis. So we start with LISA, where the low frequency we start with is 10 millihertz. We're employing a Fisher matrix analysis pipeline on LISA. And we are also using the IMR Phenom XPHM model for LISA. And then we're getting constraints on spins and masses. When we move on to ground-based detectors, we have an f-start that varies with detectors. So for example, current generation detectors, Virgo, LIGO at design sensitivities are anywhere around 10 to 12 hertz they start. And third generation detectors like Einstein telescope starts anywhere from 3 to 5 hertz. This inference is now, ground-based inference is now aware of what LISA has observed. Again, in a way, we are shrinking the prior space to size as LISA given us. And we obtain the posterior of the 6 spin components from here. Finally, we move on to the remnant analysis, for which we are using the SurfMBH pipeline, which uses a combination of numerical relativity surrogate 7DQ4 model and another surrogate 7DQ4 remnant, where the remnant model is trained specifically for analyzing merger remnants using GPR on numerical relativity simulations. Getting to our results, so we start first with looking at the recovery in the best case scenario with current generation detectors, spelled out here as HLVIK, that is Hanford, Livingston, Virgo, India, and Kagra. We see that they have a hard time distinguishing between the low recoil kick magnitude and the high recoil kick magnitude. The left one showing the low recoil kick of around 70 kilometers per second, and the right one showing it at about 1,000 kilometers per second. Basically, it's particularly blind to distinguishing between these two kick magnitudes. So LISA alone does a pretty good job of constraining one of the kicks, but not the other. And so the left one, you can see that it is doing a very good job at constraining the 70 kilometers per second kick, but is very uninformative of the higher kick magnitude. Now moving on to Einstein telescope alone, we see that it does a pretty good job on constraining both low and high recoil kicks. Not only is it able to distinguish between the two, it is giving us a very reasonable posterior to work with. Moving on to the multiband. So here we are multibanding Einstein telescope with LISA. Again, so we are running the analysis in Fisher analysis in LISA. We are getting the constraints on spins, 6 individual spins, mass ratio, putting that into the prior of Einstein telescope and then running the Bayesian inference all over again to obtain this particular plot. So you can see that this is particularly the best case scenario we have. Again, not only does it manage to distinguish the two cases, we get extremely good posteriors to work with. We also saw that this is an improvement over using ET alone, the Einstein telescope alone, or using LISA alone. The problem with using just LISA is that it does not manage to constrain the parameters for all cases. So we saw that it did a pretty good job for the low kick case, but it is blind to the magnitude of high kick case. It's pretty much similar to what we get from the HLV-IK network. So this table also supports the conclusions that HLV-IK is blind to the injected kick magnitude. With an extremely broad credible interval, LISA does fairly well for the lower kick magnitude, but fails to do the same for the higher kick case. We also observed the fact that LISA isn't performing similarly across the two cases, of course, and Einstein telescope is able to distinguish between the two cases and give us a fairly narrow credible region. But Einstein telescope working with LISA is in a league of its own. For both cases, the median manages to be fairly close to the injected value, as well as the credible regions, which are very narrow. This is the most accurate measurement of kick we can hope to do. Moving on to our conclusions. So working with two cases of kick, we concluded that the current ground-based network, even at its advanced plus design sensitivity, is largely agnostic to kick measurements, even at its best advanced plus design sensitivity. Third generation working alone shows much more promise for measuring recoil kick, but multibanding the system with LISA takes the trophy. So it is giving us the most accurate measurement of recoil kick. Since kick is just dependent on 6 spins and masses, it remains blind to all extrinsic parameters. We also studied the direction of recoil kick velocity, recovering the full velocity vector of the remnant. So not just the magnitude, but the direction as well. So we obtain constraints on kick magnitude, which of course can be used for further astrophysical analysis, placing the constraints on rate of detention in black hole binaries as well. Thank you so much.
Thank you very much for your talk. It was quite short, but that's good. We have plenty of time for discussion, and let's see if I do see a hand. So let's go ahead, Matt.
Hi, Shobit. Thanks for the talk. I wanted to ask, so why are the different detectors better for lower or higher kicks? Is there something intrinsic about high and low kicks, or is it to do with the binary parameters which produce those kicks?
Okay, so to answer that question, I'll first go back to this particular plot. So first, like the only difference between these two cases we are using is the azimuthal orientation of spins. So LISA doing better for one and doing worse for the other is, I think, only depending upon what the azimuthal orientation of spin was. So it was favorable for the antenna pattern of LISA while working with Fisher analysis. So that is one reason why it might be able to observe it better. So it's a very sweet spot case. It wouldn't apply to all spin orientations. So that is one way of showing that, you know, LISA will only do it, like it will be a roll of dice with LISA alone. But while working with others, we can be sure that, you know, we'll get a pretty good posterior for recoil kick measurements, because LISA is also putting constraint, and then independent antenna patterns across multiple detectors wouldn't depend on what kind of spin orientation we have. I hope that was able to answer your question.
Yeah, thank you.
Thank you.
Thank you. Any other questions? There's a comment in the chat that there's more degeneracy for low kicks versus high kicks. That's one of your supervisors, I think, right?
Right, yes.
Yeah, this is quickly, I just wanted to add. So there are more things that make low kicking black holes than high kicking black holes. And so the number of configurations, end up making the error bars bigger for even if it's the same detector sometimes.
Thank you. Don't see any other. So there's a question in the chat. Have you analyzed the SIGO's ability to determine kicks? I ask as it spans the gap between ground-based and other space-based interferometers. Are you aware?
Can you repeat that?
So the question is, have you looked at the detector with the sensitivity in between LISA and ET? And so one of them is a concept from Japan, the SIGO.
Yes, so I haven't actually looked at that. That will surely be something in my future works. But of course, that is a huge part of multi-banding with detectors in different frequency bands. So that will be something I'll be working on in the future for sure.
Thank you. I don't see any more questions. So let's thank Shobit again.
Thank you.
And we move to the third talk in our session by Masoud Khan from Johns Hopkins University on observability of lensing of gravitational waves from massive black hole binaries with LISA. And please, we see your slides.
Hello, everyone. Can you hear me?
Yes, go ahead.
Okay. Hello, my name is Masoud Khan. I'm a first-year graduate student at Johns Hopkins, working with Mark Kamionkowski and Emanuele Berti. I am going to discuss observability of lensing of gravitational waves from massive black hole binaries with LISA. So, as you know, the lensing of electromagnetic waves have been widely used in studies of astronomy, astrophysics, and cosmology, including in concerning the dark matter, measuring the Hubble constant, and many more studies. Now, similar to electromagnetic waves, gravitational waves can also get lensed. Now, while the principles for both phenomena are the same, there are some intriguing differences. There is the lensing of electromagnetic waves is usually treated under the geometric optics approximation, where the wavelength of the emission is much smaller than the physical size of the lens. While this may be generally true for lensing of light, that is not necessarily correct for gravitational waves. That is, if the wavelength of the emission is similar to the size of the lens, then we need to consider the wave optics effects to get a full picture of the lensing that is going on. That is, if the lens mass follows this condition that you can see here, then we need to consider the wave optics effects. Here, F is the frequency of emission of the gravitational waves, and ML is the lens mass. For an axially symmetric lens, lens mass is defined as the amount of mass that is enclosed within the Einstein radius of the lens. So it may not be necessarily the same as the total mass of the lens, but it's the mass inside the Einstein, right? So if this condition is true, then we need to consider the wave optics effects. To get the effect of lensing on gravitational wave propagation, including all these effects, we need to solve the complex value diffraction integral F, which is a function of frequency, as you can see here. So here, the capital D's are the angular diameter distances that you can see from here. The psi naught is usually the relevant scale of the problem. It's a normalization factor, which we use to choose to be the Einstein radius. Here, this integral is over all possible paths, including those that are not geodesics. The two vectors x and y that you can see here depend on the physical coordinates of the image on the lens plane, as you can see here, or the source on the source plane. Y is named the impact parameter, and it's a very important parameter in question, so please keep that in mind. TD is the time delay for a given path. So if you want to get the lens gravitational waveform in the frequency domain, you need to know that the lens gravitational waveform is the product of the unlensed waveform and the diffraction integral F. Now we look at the spherically symmetric lenses for discussion here, which then we can write it as a function of W and Y. Y is the impact parameter and W is the dimensionless frequency, which I define here. Now, luckily for us, For point mass lenses, we have an analytical solution for a long amount of time, which depends on the gamma function and the confluent hypergeometric function as a function of W and Y. For simplicity, here I write the dimensionless frequency W as a function of the redshifted lens mass MLZ and the frequency F. So for a fixed lens mass, W is a function of the gravitational wave frequency F. So we have a solution for the point mass lens. So for the singular isothermal sphere lenses, this is the form of the diffraction integral F as a function of W and Y as before. The issue is that both the exponential and also the Bessel function in the integrand can oscillate rapidly, which means that the numerical evaluation of this integral is tricky. Now, while there are several numerical approaches that have been proposed in literature, they may be costly. Therefore, they prevent us from using them in a grand scale study. Here, we propose and implement an effective method that gives us an analytical solution to this integral that is based on the Taylor expansion of the exponential factor that you can see here. Then we define the important integral In of W and Y, which luckily has an analytical solution that depends on the gamma function and the confluent hypergeometric function. Then we define the exponential factor there, the expansion. And then once we have these two things, then we can get the diffraction integral for the SIS lens in this form. Now, in the next slides, I show you the amplitude and the phase, the argument of the diffraction integral obtained for point mass lenses on the left-hand side and SIS lenses on the right-hand side as a function of dimensionless frequency W for varying impact parameter values that you can see here. So on the left side, this frequency-dependent effects that you see are diffraction effects. These are the wave optics effects. As you can see, for both amplitude and there's the amplification factor and phase, they depend on the frequency. As we increase the W, we get into this region where modulations are very high. Here is the interference regime. It's because gravitational waves are coherent and we have multiple images in this regime. And because they're coherent, they interfere with each other if the time delay caused by lensing is shorter than the duration of light, which is true for some cases with LISA. So using our analytical solutions, we can calculate the diffraction integrals for the both cases. Now let's look at the lens gravitational waves and the information matrix formalism to understand how this affects the lens gravitational wave and what we can learn from these effects. So here you see the amplitude as a function of frequency of the reduced time delay interferometry observables AET of LISA. This is because of the orbital motion of LISA around in its orbit around the sun. You see the inspiral merger and the ring down. So now this is an unlensed waveform. Now we ask the question, what if this is lensed by, first of all, point mass lens? Here we get a reference lens with 2 × 10⁷ solar masses in lens mass, and we fix the impact parameter to 1. And this is how the lensed TDI observables look in amplitude as a function of frequency. Now, if we keep everything the same, but change the lens model to the singular isothermal sphere model, this is how it looks. So the observable that you see depends on the lens mass, the impact parameter, but also the lens model that you have, and depending on that, your observable changes. Now, to perform parameter estimation, especially to get the observability of the lens parameters, we actually form our information matrices that include all the 11 source parameters that I list for you here, including 2 aligned spin parameters, as well as the 2 lens parameters, that is the redshifted lens mass and the impact parameter. Overall, our variance covariance matrices are 13 by 13 in dimensionality. For the waveform models, we use the phenomenological gravitational waveform models such as IMR phenom D for the quadrupole only case. And if you want to include the higher order modes and look at their effects, we use IMR phenom HM waveform model. The reason that we can get this is because we have analytical solutions to the diffraction integral, therefore we can get the derivatives as well. So now that we have the information matrix formalism under our belt, let's continue. So let's look at the effect of merger ring down and the higher order modes. So here I'm showing you the measurability of the relative uncertainty of the redshifted lens mass as a function of lens mass for a point mass lens that is fixed and an impact parameter 0.1 that is fixed. And here we have a reference binary with total mass about 2 × 10⁶ solar masses, mass ratio 1, and we place it at redshift 1. Now we fix the spins to be 0 for this initial case. but we randomized all the other parameters hundreds of times. And here, the high opacity line shows you the median value that we get, and the low opacity line shows us the 68% confidence interval. So here you can see the measurement uncertainty of the lens mass, and ISCO stands for here that the waveform here is the in spiral only waveform. This is the waveform that has been used in the literature before. So this result is what we have in the literature before. And this is our result, but our result matches the result in literature. But now the question is, okay, we can measure the lens mass, but what happens if we include the merger and ring down to the signal? Because this hasn't been studied before. So once we include the merger and ring down and repeat the same exercise, what we find is that adding the merger and ring down actually decreases the measurement uncertainties by almost an order of magnitude. And as a result, the lowest lens mass that we can measure also decreases by an order of magnitude. As opposed to 10 to the 5 in the previous case, now we go to the 5 times 10 to the 3. And even if you think that 100% relative uncertainty is too high, like too bad for a threshold, if you put it at 10% relative uncertainty, it changes from 10 to the 6 to about 5 times 10 to the 4. Now the question is, what happens if our waveforms also add the higher order modes? Then this is what happens. And this is a conservative choice, and a binary with mass ratio higher than 1 would here show a more drastic improvement thanks to the higher order modes. Before we move on, what we see here is that as we increase the lens mass, now we have more lensing going on, and we have frequency-dependent effects that enable us to measure the lens parameters. As we increase the lens mass, the errors decrease. At some point, we start to leave the wave optics part and hit a dip in the diffraction integral. That's where the errors increase again. But then they decrease again because we now are in the interference regime where the double images interfere with each other. And so we can measure the lens properties once again. Now, this is only for the lens mass. When we repeat this exercise for the impact parameter, we also see the similar improvements thanks to the merger and ring down. Now, if you repeat this exercise for different impact parameters, different binaries, and also for the SIS profile, the single isothermal field profile, we see the same results. I'm just showing this one as an example. Now that we understand the effect of merger and ring down and know that using in spiral only waveforms underestimates the measurability of lensing, I am moving to the effect of the source parameters. Here, for a reference binary, we fix every parameter including lens parameters, except the inclination angle in this case, and we randomly sampled about 100 times. And with the colors here, in each beige is one realization, and with blue and green, you can see the face-on and edge-on binaries. On the right-hand side, this is how the inclination affects the measurement uncertainty. It's about 20%. Variability due to the inclination angle. On the left-hand side, I show you the normalized to SNR results. Here, we normalize the measurement uncertainty to the unlensed SNR to see whether a source parameter makes an effect due to a change in the SNR or something more intrinsic. And by looking here, we see that inclination angle makes an effect, not only due to a change in the SNR, but allowing us to probably break the degeneracies by making the higher order modes more prominent. Now, when we ask the same question,
three more minutes.
All right, thank you. For component spins, we see that they make a 50% effect, and also in the normalized SNR case, they also make an effect. Now that we have this understanding, we do look at the measurement of the lens mass and the impact parameter in a wide range of the lens parameter space. On the horizontal line, you have the redshifted lens mass, and on the vertical line, you have the impact parameter. For a select binary, the colorful areas is where we can measure the lens parameters. As you can see, the lens parameters are measurable thanks to the wave optics effects in a wide region of the parameter space. And because of the merger and ring down, these limits are way higher. Now, if we keep everything the same, but change the lens model to SIS, this is how it looks. Now, there's one important part here, that is the highest measurable impact parameter that we have here is not a constant as it was believed in the literature before, but it's a function of the lens mass. So an accurate study of lensing probability needs to consider a case-by-case basis of a lensing situation with the lens and source population. But overall, what we find is that including the higher order modes, merger and ring downs enable us to measure lens parameters in a wide range of the parameter space. Now we repeat this exercise for other select binaries that you can see here on the left-hand side, measurability of lens mass and impact parameter on the right-hand side for different binaries in each row. In each case, we have a wide range that gives us measurable lensing. To summarize the results, here I show you a table in which you can see the critical impact parameter, highest one that we can measure, or the lowest lens mass that we can measure for different binaries. Now, we also repeat this exercise for the SIS lenses, and again, I show you the final results. Again, what we find is that we can measure lensing up to very high impact parameters and up to lower than previously thought lens masses. Now, let's conclude. So first, what we know is that wave optics effects in the lens gravitational wave signals are vital. They cannot be ignored. Frequency-dependent wave optics effects could lead to a plethora of applications such as precision tests of cosmology. You can use for the time delay cosmography. You can maybe use them to constrain the lens population because they enable us to actually measure the lens parameters directly. Now, this is to our knowledge, the first study that utilizes the analytical solutions and derivatives of the lens and diffraction integral for the SIS lenses. And it's also the first study using gravitational wave models that include the merger, ring down, higher order modes, and aligned spins. I also want to mention that it's also possible to use these wave optics effects to break the mass sheet degeneracy, but which is to be studied. Now, we find that in spiral-only waveforms used in the previous studies overestimate the measurement uncertainties in the lens parameters by about an order of magnitude, and then merged ring down on higher order modes significantly improve our ability to measure the lens parameters. And while we may need to consider, because we can measure really high lens parameters, maybe more than one lens in the line of sight with the impact parameters small enough. Maybe we need to consider line of sight halo contributions and maybe other complexities. We may need to improve our analysis for other lens models such as NFW. But nonetheless, wave optics effects gives us a great powerful tool to learn about the lenses and the sources. And regardless of any of these, a new era of lensing studies is waiting for us, thanks to wave optics effects. Thank you.
Thank you very much. That was well timed. Almost beginning to wonder why I'm chairing this session anyway, because all the talks are on time. Anyway, that's great. Any questions? Either raise your hand or type them in the chat or in the chat of the live stream. Well, there are no questions yet. Let me then ask the first question. So for lay people like me, can you give some indication how this maximum value of y relates to sort of a probability of lensing?
Oh, very great question. So for the lensing of light, the maximum impact parameter y value that you can get that information is 1. And lensing probability is proportional to the square of the impact parameter. So even if you cannot measure lensing up to 50, but let's say 10, that means that the lensing probability would be 100 times that of strong lensing. So even if the rates of the massive black hole binaries are low and that we don't expect that many strongly lensed systems, let's say we expect 5 or 6, and I know Alberto Cesana is in the audience today and he had a paper on it about 10 years ago with Sereno. What is important is that by measuring high impact parameters, you actually increase your lensing probability by a lot. That is the square of the impact parameter. That's how it is proportional.
Thank you. So there's a question. Do you expect the lens parameters to be degenerate with mass or spin? How much do we expect the errors to degrade?
Okay, so in our variance covariance matrices, we look at the variance and also covariance between all the mass and spin parameters. So spins, the aligned spins are included. Actually, including these parameters do help. There is some degeneracy when the lens mass and is very low or impact parameter is very high. But our study includes 4 possible degeneracies between by including all these parameters. Now, I don't know whether eccentricity, etc., and how they would affect, though they need to be studied. If I understand the question correctly.
I think yes, because
thank you, Marco.
Question: can you elaborate on how this can break the mass sheet degeneracy?
Yes, so I think what happens is that in a portion of the wave optics regime where the lensing is strong enough and interference regime starts, where you have these double images interfering with each other, Cremonese and Jose Maria Esquiayo, Jose is at the University of Chicago, they looked and then they seen that you may have enough information to do parameter estimation, let's say on directly the lens mass, not the redshifted lens mass and the lens redshift. But this is one of the things that I want to try now and see whether we can actually estimate the lens mass. So to what accurately this can be done, we don't know, but we know that in this small regime that I showed you today, you may have enough information in your signal to actually measure these parameters directly instead of measuring the redshifted lens mass or impact parameter. You may look for physical parameters and try to measure them, but we don't know how well they will measure. This is a question of a next study. Thank you, Alexander.
All right, thank you. Don't see any more questions. We still have 2 minutes, so let me ask then my other layman question, which sort of precedes all this. So, but you can recognize that you're dealing with a lensed signal rather than a more distant, more massive one, like we had some discussion with the ground-based detectors.
Yes, well, I think that's one comes from, maybe I can go back a little bit, because if we had, let's say in the lensing of light, you have that full degeneracy between the two. Then if you had lensing, your signal would just basically get bumped as a frequency independent way, and your phase will be either the same or be shifted by an integer multiple of pi over 4. But when you have this wave optics effects, this is how your signal changes. It changes in both amplitude, which I show here, but also in phase in a frequency dependent fashion. And then you get to see these modulations, which are very different than what you would have if you were completely in this, strong lensing regime without these wave optics effects. But now there's a question, can any other thing replicate this, or do you have the correct lens model? These needs to be more carefully thought. And one improvement, for example, would be to do this study not on a, let's say, not on an SIS lens, but NFW lens, or maybe push this further so that we have a template bank for many kinds of lenses, not only these two.
Hey, I can't hear you there.
Yes, I couldn't hear either.
We had that yesterday too. Can you hear me now?
Yes, that's better. Thank you.
All right. So let's thank the speaker again. We move to the last talk of this session by Jordi Davila from Columbia and Flatiron Institute on probing black hole shadows via electromagnetic self-lensing flares. Go ahead, Jordi.
Thank you very much, Gijs. Yeah, so it's a nice step from gravitational wave lensing to electromagnetic lensing. So this is a project that I worked on together with Zoltan Heyman here at Columbia and the Flatiron Institute. And well, let me first elaborate why we think it's important to look for self-lensing signals from black hole binaries in general. So let's see, watch this. So currently there are around 150 black hole binary candidates, supermassive black hole binary candidates found via large time domain surveys. However, these are typically found by looking for periodicity in their light curves. And this can be degenerate with, for example, just your vanilla AGN accretion variability, which follows a random walk behavior. So one way to lift this degeneracy between a single black hole and a double black hole is to look for events where one of the black holes is actually lensing the background black hole, which amplifies the amount of emission very rapidly and will give a very clear signature in your light curve. So out of these 150 candidates, there's actually one very peculiar candidate who was found in the Kepler data in 2010 already. This candidate is called Spiky, and I show it here on the right side of my slide. So here in black is the Kepler data. And as you can see, it follows some kind of a sawtooth pattern, which is quite typical for orbits who are eccentric. So then the Doppler boosted signal becomes more of a sawtooth-like pattern. And the magnification is plotted here as a function of time. And the moment that you expect the two black holes to line up along the line of sight, there is this massive increase of emission that is observed by Kepler. So one of the ways that people explain this is that indeed the two black holes are in front of each other. The foreground black hole acts like a lens and enhances the emission that we observe. However, this type of effects are typically studied with microlensing approximations, which is a nice way of doing this because it's a simple analytical formula that you can just easily apply on some like point source style source model, and then you can easily go over a large set of parameters. However, we can expect that like the source morphology, the morphology of the emission region is also affected by like GR effects. So the way the black hole looks like, we need to take into account also GR. So why is this important for example, LISA? Well, if we know how these self-lensing flares look like, we can use, for example, ground-based facilities to look for these features so that we can improve sky localization by looking for these spikes. And if we actually measure such a self-lensing flare together with a gravitational wave signal, we can even match the phase of the electromagnetic signal with the gravitational wave signal, which could, for example, allow for graviton mass estimates, as it was explained in the paper by Heyman 2017. So that brings me to the motivation of this study. So our goal is to study these self-lensing flares with general relativistic ray tracing. So general relativistic ray tracing is a methodology where we have some virtual camera somewhere out of our domain of interest, and this camera has a variety of pixels. Every pixel is assigned a wave vector, which we then use to solve the geodesic equation. So the geodesics that we obtain can then be used to solve the radiation transport equation, and therefore we know how much emission arrives on the camera for every single one of these pixels. So for our study, we used a ray tracing code that I developed during my PhD program in the Netherlands, which is called Raptor. So the physical model that we used is here shown on the right as a nice cartoon. So the binary is on a Keplerian orbit. Every black hole has its own mini disk, which is prescribed by a Novikov-Thorne style emission profile. So it's a razor thin slab of emission in the equatorial plane. So this binary can be eccentric. It can have varying mass ratios. It can have different separation radii ranging from 100 gravitational radii all the way up to 1,000 gravitational radii. And so we did like a parameter study of how these model parameters affect the self-lensing feature. In total, we have 27 different models in the two papers that we published. But of course, sadly, like in the roughly 10 minutes that I still have left, it's of course impossible to go over all 27 of them. So I'll try to focus on the most important result that we obtained in this work. So first, let us all get a little bit more familiar to how these black hole images look like. So this is a nice visualization by Jeremy Schneepan from NASA, who did a similar ray tracing of an individual black hole. So what you see here is like this thin disk that is like orbiting around the black hole. There is lensing happening on the top and on the bottom part of the black hole. This is why you see this emission also above the black hole, which is here in the center, due to the strong curvature of space-time. So there is some Doppler boosting happening as well. So the left side is moving towards the observer, the right side moving away, so it's enhanced. Additionally, there's this photon ring, which is a critical curve where geodesics start to orbit around the black hole and catch up more and more emission. So this is like typically also a strong feature within these images. And in the center is the black hole shadow, which is also known as the apparent size of a black hole on the sky for a faraway observer. And the size of this black hole shadow is very tightly constrained by general relativity. So measuring a black hole shadow, and if you know the mass from a different mechanism, would help to like constrain general relativity. And this is of course also like one of the main goals, for example, of the Event Horizon Telescope collaboration. So let's show one of the models that we produced. So this is a black hole binary shown at 87 degrees, where 90 means perfectly edge on, so perfectly perpendicular with the orbital axis of the binary. The binary has a separation of around 100 gravitational radii. It's an equal mass system. It's a completely optically thick system, which means that there is no photon ring. So the disk actually extends all the way to the horizon. So photons don't have the ability to orbit around the black hole for more than one time. And this is an image generated at a soft X-ray band. So if we then start to play this movie, it will become clear why it's called a self-lensing flare, because the binary self-lenses itself. So the foreground black hole amplifies the background black hole, and it hugs around the foreground black hole, creating like this Einstein ring like feature. So yeah, this is what it looks like. Well, these quasars are of course typically quite far away, so there seems to be no hope of course generating a real image of such an event, but we can still look at light curves. So, and this is for example an example for a viewing angle of 90 degrees. So this is perfectly edge on a view of the binary with the same parameters as I described earlier in the previous slide. So in this case, you see again that you get like this nice Einstein ring around the foreground black hole. So and here on the bottom, I now also show the light as a function of phase in the orbit. This is like normalized flux. So initially, everything is just nicely quiescent. And at the moment these two black holes line up, there is this increase in the amount of emission that you observe. But additionally, like most of the works in the literature only show a single individual spike without substructure. And in our work, we actually found that within this flare, there is some additional substructure, namely like this dipping cell feature that we see in both of these flares. And this seems to happen when the focal point of your foreground lens moves over the ring-shaped feature of the black hole in the back. So as the focal point moves over the left, there is emission that it can amplify. If it is in the center on top of the black hole shadow, there is no emission to amplify anymore. And on the right side, it's back on this ring again, and there is like an enhancement in flux. So this made me thinking, like, does this dipping feature then also nicely correlate with the black hole shadow size? And that seems to be the case. So what we did is we measured the duration of the dip in our light curve. And if you know how long the duration is, and you multiply this by the total circumference of your actual binary, I got a number 10.4 times the gravitational radius. And as a person who was also active within the Event Horizon Telescope, this immediately started ringing all kinds of bells, because this is the black hole shadow size diameter. So there seems to be a very nice correlation between how wide this feature is and how large the black hole is on the sky. And this is interesting because this can potentially then be used to find black hole shadows that are unresolvable by current VLBI techniques, because we don't have to resolve the source spatially. We just need to resolve the light curve time-wise well enough so that we can sample it good enough to measure the width of this dip at high enough accuracy. But of course, this was a perfect example, and the perfect world doesn't really exist. Like, the odds of seeing the binary exactly edge on is of course quite slim. So what about if you're slightly further off the equatorial plane? So how does it depend on inclination? So these light curves as a function of inclination I show here on the right. So the red one is again perfect edge on view, 90 degrees, and then we alter it all the way to 80 degrees here in black. So as the focal point moves further and further away from the source, the amplification efficiency starts to drop. But additionally, also the focal point does not move anymore over this ring-shaped feature. And you start seeing that like the width starts to slightly shrink because you pass over the circle at a different altitude. So effectively your diameter becomes smaller. And around, what is it, like 87 degrees, you start to not go over this shadow-like feature anymore. So for this particular setup, we have like a window of like roughly like 3 degrees. That it could be possible to get some information on the fact that one, there is a shadow, and two, like on its actual size. So we can also do some analytical estimates then. For example, if you take just the ratio between the shadow diameter and the circumference of the actual binary, this is like what I would expect this signal to look like. You can plug in Kepler's third law and then plug in the binary mass, the binary period, and the mass ratio. And then you actually also get the exact same number that we get out of our ray tracing simulation. So the size is nicely consistent with this simple analytical prediction. But this also means that we can plot how large the window of this phase, or how big the phase is as a function of orbital time. And as the orbit becomes wider and wider, the velocity drops, so the binary moves slower. So the focal point moves slower over the background image, and the window becomes larger as well. So for LISA, this would mean like if we go to like shorter and shorter periods, the dip will become narrower and narrower. But however, the inclination window also grows because the size of the black hole as seen by the lens becomes larger and larger as well, because these black holes are just closer by. So this makes it on one way easier to measure because there's a larger window for it to be observable. But on the other hand, we will need higher and higher time resolution to actually sample this light curve. Sufficient. Yes.
3 more minutes, or 2.5 by now.
2.5 minutes. Okay, that's perfect. So what about search strategies? So the inclination window is quite small, but if we look at the current sample of black hole binaries, they're typically skewed more to the high mass end, so like 10 to the 9 solar masses. So this dip would and they have periods of around a year. So if we plug all of these parameters in our formula, then like the dips would take a couple of days and the inclination window is a couple of degrees at most. So the probability of finding this dip in the current data, if you assume a uniform distribution of inclinations on the sky, is around 1%. So first strategy would, of course, be to just follow up on the current candidates that we have, which are 150. So who knows, there might be one in there already. And of course, like as was explained by Cheng earlier today, for Rubens Observatory, LSST will see like 100 million quasar targets. So we could also just look at that sample and might be something in there as well. And additionally, of course, interesting for this audience is to look at pre-merger electromagnetic emission for LISA sources, which will then help looking at these spikes for sky localization and might give even some information about the black hole shadow size. So there is some preliminary outlook, like we are currently looking with a grad student here at Columbia, Luke Krauf, at like how, because we're using the Stoy model, the simple analytical profile for the emission. So what would happen if we use a hydro code, which actually tells us how the matter moves around these black holes to get a better handle on the spectral shape, on velocities. We will then also include the circumbinary disk as a potential blockage towards the inner part of the binary, add additional accretion variability to figure out if this feature still survives above the noise of all the accretion whirling around, and if we could maybe then use phase folding, for example, to get rid of the time varying features and just get the only time consistent feature, namely the self-lensing flare. Well, given the time, I will leave my summary and outlook up, but yeah, I think it's an intriguing mechanism that could potentially be useful for LISA for sky localization or graviton mass measurements, or even black hole size estimates for sources that are way out of reach by VLBI techniques by the Event Horizon Telescope. And I'm happy to take any questions either now or via email.
All right. Thank you very much. And so let's see if there are any questions in the chat. Raise your hand in the participant list with the raise hand button, or questions from the live stream. I think there's still only clapping hands for now. Anybody? Jordi and I have been having some conversations about this already, but let's still see if there's anybody else. Okay, if not, then I'll go. So in the 150 candidates that you have now, do you think there's any inclination bias?
Yeah, Yeah, there is inclination bias because they are found via their periodicity. So there should already be some Doppler boosted signal, right? So these sources are typically viewed more axon than phase-on because they are found via Doppler modulations. So this percent number that I gave is a little bit on the pessimistic side, even like it could be higher, given that these are found more closer to axon than phase-on.
That's good.
Yeah, but one thing to maybe mention is also like there is also of course mass ratio here, so that might like make things harder again, because I only showed here like equal masses. Like if the black hole becomes smaller on the sky, it will also be harder to observe it again. So there is some competition with a lot of different things.
All right, well, I think we've had this discussion about equal masses. You know my opinion on equal masses. It's a very bad idea. I see no other hands. I'm sure that's not because, well, maybe it's because the talk was so clear, or everybody already read the two papers, then that's the other option. All right, let's wrap up here and thank all the speakers of this session. We went from accreting white dwarfs to supermassive black hole binaries to quite detailed things about lensing, etc., etc. I certainly enjoyed it a lot. Thank you all for keeping well within time, which means that we end this session even 10 minutes before the end. We have a slightly long break. I wish you all a good break. I hope to see you back at the other sessions today, which start 8 o'clock our Central European summertime, which is 2.5 hours from now. Rona, are there any other technical or other things we should say?
No, I am pretty much the same. I was just going to thank you for chairing so well, and thank all the speakers again. All the talks were brilliant, and I hope the audience enjoyed them all. Yes, so enjoy the 2.5 hour break. The plenaries tonight are a bit lighter and less technical, and should be enjoyable as well. So see you all back then.
Bye bye.
Thank you. Bye.
Thank you.